Section 3.2 and 3.3 together, what is that about? Inverse transforms and transforms of derivatives. So we're going to find inverse Laplace transform of elementary functions. We will find the inverse Laplace transform using kind of a trick. I'm going to show you. It's not a trick, it's an actual result from complex analysis. Find the Laplace transform of derivatives and use it to solve differential equation. Okay, so if we take the Laplace transform of a function f of s, uh, if we take now, we're going to take the inverse transform of a function of s to get back to the original function of t. And guys, we're going to use exactly the same formulas, except that we may need to do a couple of tricks here and there. All right. What else? The linearity property holds the same. The inverse transform of a sum of two or more functions that get multiplied even by a constant, well, we can take the inverse transform individually, which is essentially what we're going to do. All right. I mean, that being said, let's just use the formulas. Find the inverse transform of 1 over s to the fifth power plus s squared plus 7. Okay, so number one, so I'm going to do the following. I'm going to leave some space in here. Okay, check. So this is the inverse Laplace transform of 1 over s to the fifth power. Okay, plus some space, inverse transform of, um, what is that? 1, also 1 over s squared plus 7. Okay, guys. So we need to go from a function. Okay, this looks like an S. Let me make this look like a 5. There we go. Okay. So uh we need to go from the world of S back to the world of T. Now, the tricky part right here is to identify what n plus 1 is. All right. In this case, the quantity n plus 1 equals to 5, isn't it? That means n equals to 4, which is the factorial that has to be here in the numerator in order to be able to find the inverse transform. We cannot just evaluate the inverse transform if we don't have a complete expression. We need to make sure we have the factorial of n. However, 1 doesn't look like 4 factorial, does it? So we wished we had a 4 factorial there. We can make our wish come true. Okay, multiply numerator by 4 factorial and divide by 4 factorial outside of the Laplace transform. All right. So what about the next? What about the next? What is that? What about the next term? Okay, so we have 1 over s squared plus 7. So we have a number here. We don't have the variable s. So that actually looks like we're finding the inverse transform to get back to the sine function, don't we? So, but this is not a complete expression. In this case, check this out. K squared, the quantity k squared equals to 7. That means k equals to square root of 7. And in the numerator, we only have a 1. We don't have a complete expression. We need to make sure that we have that k there. We don't have it, but again, we can make our wish come true by multiplying in the numerator by the square root of 7, provided you divide 1 out in front of the Laplace transform, the inverse Laplace transform symbol. That being said, we're ready to go. All right. We have a complete expression, 4 factorial over s to the fifth power, that is 1 over 4 factorial, which is 24, t to the fourth power plus 1 over root of 7 sine root of 7 t. Final answer. Right? That is how we find an inverse transform. So it's not just, using the formula. We want to make sure we have a complete expression. All right. That being said, let's have a look at the next example. The next example is a rational expression with two terms in the numerator. So what I would like to do here is to split this into two. So this will be the inverse transform of 6 over s squared plus 4 minus the inverse transform of 2s over s squared plus 4. All right? In this case, we're going to use two formulas in one shot. Actually, let me take out the coefficients outside of the 6 and the 2 here. So this is 2 times the inverse transform of 1 over s squared plus 4. And can we make some space in here? Okay. Plus, or rather, no, minus 2 times, okay, minus 2 times the inverse transform of s over s squared plus 4. Well, in this case, actually, we're going to, like I mentioned before, we're going to be using both inverse transform formulas, that of sine in the first case and that of cosine in the second case, because look at the form, a constant over s squared plus k squared, and then s, not a constant, over s squared plus k squared right here. All right? So, but here again, what's k squared? So k squared equals to 4. That means k equals to 2. Well, we wish we had a 2, but actually only in the first one. We oh, well, actually this is supposed to be a 6 over 2. Okay, this is supposed to be a 6 right here. All right. And well, 6 divided by 2, isn't that equal to 3? And this is the inverse transform of sine of 2t minus 2 times the inverse transform of cosine of this expression rather, which is cosine of 2t as well. All right. So that was another example. Okay, let's do a couple more actually. Let's do a few more. Okay, so inverse transform of s to the negative 3 halves. All right. Well, we can't have factorials of rational numbers or of fractions like this. However, we have a powerful tool called the gamma function to get this transform. Okay, let me actually state the inverse transform of a power function in terms of the gamma function. So the inverse transform of n factorial over s to the n plus 1, okay? This is the same as saying the inverse transform of gamma of n plus 1 over s to the n plus 1, all right? Which is going to be t to the n. So we're going to need this one. Also, I'm going to need the gamma function, okay? So for the gamma function, that's gamma of n plus 1 equals to n gamma of n, all right? Two pieces of information we need to before getting through this one right here. All right. So, number one, this is the same as saying, okay, this is the same as finding the inverse transform of 1 over s to the 3 halves. All right. But what is s to the 3 halves? Do you guys agree that that 3 halves is the same as 1 half plus 1? All right. That's 1 half plus 1. Okay, well, so how about we evaluate gamma of 3 halves? Okay, let me do some let me do a side trip here. So gamma of 3 halves equals to gamma of 1 half plus 1, which at the same time using the definition, that's n gamma of n. In other words, take the 1 half outside and that equals 1 half gamma of 1 half, which is gamma of a half, isn't that the square root of pi from last time or a couple times ago? Can remember? Yeah, I think it was last time. Yeah. So, okay, so we have everything we need. All right. So here is the thing. We wished. So I mean, we can't. At this point, we can't just find the inverse transform the way it is like this. So I'm gonna make some space here. Inverse transform of uh, 1 over s to the 1 half plus 1. Okay, I'm going to break it out break it up as a 1/2 plus 1 rather than 3/2. And this just to relate with the fact that we need this gamma function in the numerator. But I mean, again, we don't have it. We wish we had it. We can make our wish come true. 1/2 plus 1, okay, provided you divide 1 out. Gamma of 1/2 plus 1. All right. Well, what's gamma of 1/2 plus 1? Didn't we already find it here? That is 1 over 1/2 root of pi times t to the 1/2. All right. In this case, n is a half, t to the 1/2. Of course, let me actually write this in a nicer way. So this is dividing by a fraction. It's the same as multiplying by the reciprocal. So this is 2 t to the half, which is root of t, divided by root of pi. And if you prefer, this is 2 times the square root of t over pi. Final answer. All right. Yeah, if you ever get a gamma function of something larger than 3/2, like 7 pi, you would have to do multiple recursions of this gamma function process, right? So, and in the end, you will end up with a multiple of a fractional multiple of square root of pi. Okay, all right, buckle up for this one. The inverse transform of 26 divided by s plus 3 of times s to the fourth power. All right. Well, so in this case, we're going to use partial fraction decomposition. Let's have a look at this fraction. Let's have, particularly to the denominators. Well, the denominator is comprised by a product between a linear factor and a quadratic irreducible factor. So I'm going to do the following. So we're going to find the inverse transform of a over s plus 3, all right? Oops, plus 3 plus bx plus c over s squared plus, oh, not bs plus c, bs plus c over s squared plus 4, all right? So, well, partial fraction decomposition. Let me use a different color for that. Okay, let me set this quantity, 26 over s plus 3 times s squared plus 4 equal to uh, the same quantity, a over s plus 3 plus bs plus c over s squared plus 4. Okay, so you want to simplify this rational equation by multiplying both sides by the least common denominator, provided we have already factored all the denominators, which in this case we already have it in the most factor form. So all we need to do here is multiply by the LCD, which is the product of these two factors, isn't it? So let me make more space. So this would be s plus 3, s squared plus 4, uh, s plus 3, s squared plus 4, okay? While distributing, that actually cancels everything in the denominator, leaving us with a 26 on the left-hand side. And then distributing, check this out, distributing these two factors over the first fraction. Do you guys see how the s plus 3's get canceled, leaving us with a times, with a times s squared plus 4, all right? The s plus 3 is canceled. We're end up with a times s plus 4, right? Because multiplication, division, cancel out. A times s squared plus 4. Likewise, we're going to cancel s squared plus 4, ending up with bs plus c times s plus 3. Okay? So the second distribution, I'm going to repeat that. The second distribution cancels the s squared plus 4s. Okay? That equals, oh, well, not equals, plus bs plus c times s plus 3. All right? And this is the basic equation, what we call a basic equation that we're going to use to find the coefficients a, b, and c. Well, the way we go about these basic equations, again, back from calculus 2, when you were doing integration using partial fraction decomposition, we would look for smart numbers. What do we mean by smart numbers? Numbers that make a whole term equal to zero, uh, that allows us to find one of the values of one of the coefficients a, b, or c. And in this case, we can see that if we substitute s equals to -3, this whole term goes away, right? Goes away to zero, allowing us to calculate the coefficient a. All right. So what about it? So let's do that. Okay. So for s equals to -3, what do we have? 26 equals to a times -3 squared plus 4 plus b times -3 plus c times -3 plus 3. Okay? What happens here? Goes all the way to 0, all right? And we end up with calculating the value of a. So 26 equals to a times, what is that? 9 plus 4, is that 13? 13a, and a equals to 2, all right? Okay, so usually we can keep doing this smart number using when all of these factors in the denominators are linear. However, we have a quadratic irreducible, and if we think about it, there's no other way to get the other constants b or c. So this is what we're gonna do. Okay, guys, I'm gonna choose a any number. All right. Why can I choose any number? Because if I substitute that number s on one side of the equation and substituting it on the other side of the equation, it doesn't affect because I'm doing exactly the same on both sides of the equation. Well, still, the left-hand side doesn't have any variables, which is what makes it even simpler. For s equals to 0, I'm going to do s equals to 0, all right? I'm just going to do s equals to 0. So this is going to leave us with 26 equals to a times 0 squared plus 4 plus b times 0 plus c times 0 plus 3, right? Well, this is going to make the b equals to 0. Cancel out the 0, the b, right? So that's why I chose 0, right? So that's one. But also it's going to leave us with the letter c. And even though it leaves us with the letter A, didn't we already calculate A before in the previous step? Okay, so for S equals to 0 and A equals to 2, you may be able to substitute 26, wait, 26 equals to uh, A, well, this is 4A plus b times 0, which is 0, and then 0 plus 3, which is 3, 3 times whatever we are left with here, which is just a c, that's plus 3c. All right? So substituting a equals to 2, 26 equals to 4 times 2 plus 3c, 4 times 2, which is 8. So 26 equals to 8 plus 3c. Subtract 8 from 26. Isn't that 18? So 3c equals to 18. And what is that? What's next? And c equals to 6. All right. And we're gonna do one more. All right. Okay, guys. We already found. Okay, check. We already found the value of c. We already found the value of a. We just need to find the value of b, but there's no way we can find the value of b just using a smart number. But we can do the same approach as we did with the previous case. Of course, I'm not going to use the value of s equals to 0 because I already used it. And it already canceled the b to 0, right? So we can try s equals to 1, a number actually that we haven't used before. All right. So I'm going to do, okay, for, I'm going to do that here for s equals to 1. And we already have, what else do we have? A equals to 2 and c equals to 6. Okay, let me actually make this one look like a 6. Doesn't look like, okay, there you go. All right, so I'm going to substitute all of this into the basic equation here. So that is 26 equals to a, which is 2, times s, which is 1 squared, plus 4, plus b times, which is what we want to know, times s, which is 1, plus c, which is 6, times 1, which is s, plus 3. With this, we should be able to get the value for b. All right, so 26 equals to 4 plus 1, is that equal to 5 times 2? Is that equal to 10? And b times 1, which is b, plus 6, that times 1 plus 3. But what's 1 plus 3? Isn't that 4? And well, let's actually, let me distribute. 26 equals to 10 plus 4b plus 4 times 6, which is 24. 24 plus 10, is that equal to 4b plus 34 equals to 26. Subtracting 34 from both sides, we get 4b equals to negative 8, and b finally equals to negative 2. All right. So we're going to go ahead and finally find the inverse transform of the given function. Okay. So now I'm going to go back to the partial fraction decomposition and get the and substitute the coefficients. Okay. So a, which is, so we'll find the inverse transform of, what was a? Isn't that 2? 2 over s plus 3 plus b. What was b? B equals negative 2 and plus 6. So minus 2s plus 6 over s squared plus 4. All right? Over s squared plus 4. Okay, so what about this one? Okay, I don't think I'm going to have enough space here. So now let's find the inverse transform of this. Well, number one, we're going to we're going to use the linear property to inverse transform of 1 over s plus 3. And then this one, this second term, this fraction, I'm going to split it in two fractions. Okay, that is minus 2 inverse transform of s over s squared plus 4 and minus, oh no, plus 6 times the inverse transform of 1 over s squared plus 4. All right. Well, there's not much to do here because did you guys agree that s plus 3 equals is the same as saying s minus negative 3? This is just so we can adapt this to our formula because the inverse transform that gives us the exponential function is 1 over s minus a, which is e to the at. So in this case, our exponent, the coefficient a in the exponential would be negative, all right, along with its coefficient, okay? So this will be equal to, what is that? 2 times e to the negative 3t, okay? What about here? S over s squared plus 4. When you have the s over the quadratic, you don't need to fix anything, any coefficients. That goes straight to negative 2 cosine of 2t. Because why 2t? Because in this case, k squared equals to 4. That means k equals to 2. All right? However, that's not going to be the case for the very last term because this is a term that will yield as an inverse transform the sine function. So we wished we had a 2 that is the square root of this number. We can make our wish come true by multiplying the number provided you divide it out in front of it. All right. All right. So 6 divided by 3, that equals to 2. So that's plus 2 sine 2t. And that's the inverse transform, finally. All right? Oh, yes. Which one? Yeah, that's what I meant, right? Divided by 2, which is 3, right? Yes. Thank you, thank you, thank you. All right. Okay, guys. The next example, the next topic. I mean, in many inverse transforms, guys, we will need to do a lot of partial fraction decomposition. However, if your factors are linear and distinct and not repeated, let me show you this trick, which is a result of a special theorem in complex analysis. It's called Heaviside expansion. All right, so whenever we have, check this out, whenever we have the inverse transform of a rational function of the form P of S over Q of S, the inverse transform would be the sum of so we will factor this polynomial in the denominator. We're gonna have some numbers there as well. That'll be the numerator evaluated at the zeros of the denominator divided by the derivative of the denominator evaluated at those zeros. Well, at first glance, this formula looks like, what the hell is this? Well, let me show you. It's actually easier than it looks. All right. So let's use Heaviside expansion to evaluate the inverse transform of this madness here, right? I mean, think about that one. That would have looked like a huge partial fraction decomposition, but actually, this would have been a nicer example of a partial fraction because all factors are linear. We can easily see that the zeros are in the denominator are 1, 2, and -4, right? We can do the work easily. But let me show you this alternative. Okay, so uh, here S equals to 1 is a 0 in the denominator. Again, S equals to negative x equals to 2 is the 0 of the denominator, and S equals to -4 is a 0 in the denominator. All right. So what are we going to do? We will evaluate the numerator at 1 divided by q prime at 1 e to the 1 times t plus the numerator evaluated at 2 divided by the derivative of the denominator at 2 times e to the 2t plus the numerator evaluated at 4 divided by the derivative of the denominator evaluated at 4 as well, e to the -4. So we essentially had set up the inverse transform, right? Okay, now let's compute the following. Okay, so what's Q of S in this case? Q of S equals the product of these three factors, S minus 1, S minus 2, and S plus 4. All right? Well, you don't want to differentiate this function while you have three factors, right? I mean, you can use a triple product rule, that's fine. But my advice here is to uh, expand all this, right? I'm going to give you the result of the expansion. So FOIL, and then whatever you get from foiling these two, multiply by S plus 4, Q of S equals to S cubed plus, what is that? S squared minus 10s plus 8, okay? And then, what is that? P of S equals to S squared plus 6s plus 9. And guys, do you guys agree that this is a perfect square trinomial? P of S equals to S plus 3 quantity squared, okay? Whenever you can keep doing this factoring, guys, go ahead and do it. Would be maybe a lot of you, maybe a lot useful, all right? Okay. I'm going to take the derivative of this polynomial, q prime. Q prime of s equals to 3s squared plus 2s minus 10. Okay. And what are we going to do here? Okay. So we're going to evaluate these two for each of the zeros in the denominator. That's to get p of 1, p of 2, p of -4, and the derivative of q at those same values. All right. So p of 1, that equals 1 plus 3 squared, which is 4 squared, that's 16. P of 2 equals 2 plus 3, quantity squared, equals to 2 plus 3, which is 5. 5 squared is in that 25. And then P of 3, that equals, well, no, not P of 3, P of negative 4, right? That is negative 4 plus 3 squared. Negative 4 plus 3, is that negative 1? 1 squared, negative 1 squared equals to positive 1. So you got the numerators here, 1, 2, 3. Now let's get the denominators by evaluating the derivative of q prime at 1. That is 3 times 1 squared plus 2 times 1 minus 10. Q prime of 2 equals 3 times 2 plus 2 times 2 minus 10. And q prime at negative 4, which is 3 times negative 4 squared plus 2 times negative 4 minus 10. All right, let's simplify all these quantities here. So, well, not this one. So that is 1 times 3 plus 2, is that 5? 5 minus 10, is that negative 5? And 2 squared, which is 4. 4 times 3, is that equal to 12? 12 plus 4, is that 16? And 16 minus 10, is that 6? Negative 4 squared, is that 16? 16 times 3, is that 48? 48 plus negative 8, that's 40 minus 10, is that equal to 30? All right. And we're done. So P of 1, which is 16 over Q of 1, negative 5, e to the 1 times t, e to the t. And what is that? 25 plus 25 divided by 6, e to the 2t. And finally, 1 plus 1 over 30, e to the negative 4t. And well, let me put the negative in the front, and that's the inverse transform. All right. Okay. So guys, again, use this method. Well, actually, one of the take-home quiz question is going to be using this method. So I'm still trying to figure this out, this same method for other kinds of rational expressions where we have, for instance, repeated factors and also quadratic irreducible. But because for the quadratic irreducible, the zeros happen to be complex. And well, I'm still having a hard time to make this work for those. But that's a topic to be developed, all right? So, but at least you guys have like the beginning, which is the one that works nicely for the denominator having linear, non-linear, and distinct factors. Yes. What you just mentioned. That being said, let's look at the second part of the section. That's essentially the 3.3 part, transforms of derivatives. Well, so now we have the what's it called? The transform of some elementary functions like polynomial functions, exponential base e, and sine, cosine, hyperbolics, right? But what about transforms of derivatives? Well, actually, we're going to use this to find or actually to solve differential equations using this these derivatives, right? Okay, so the Laplace transform of the nth derivative of the function of t would be s to the n f of s minus s to the n minus 1 f of 0 minus s to the n minus 2 f prime of 0, etc., 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 until we get to f to the nth minus 1 derivative evaluated at 0. You look at this and like, what the hell is this? Well, let's go one case at a time, first of all, and then I'm going to prove this result. We'll derive these results, okay? So that's it. That is the Laplace transform of the first derivative, that is s f of s minus f of 0. The Laplace transform of the second derivative, that's s squared f of s minus s f of 0 minus f prime evaluated at 0. Um, the transform of the third derivative, that is s cubed f of s minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. Do you see how this is the second derivative, which is one order less than what we're trying to find for its derivative? So that explains this last term right here, all right? Okay, but how do we get these ones? So letter A, this is the transform of f prime of t. All right, that is the integral from 0 to infinity of e to the negative st f prime of t dt. Okay, well, in this case, I'm going to use integration by parts to evaluate this integral. All right, so that is u equals to the f prime of t. All right, no, wait, the exponential. I know if we go Liate here, we don't know what f prime of t is, right? To like so, but in this case, I'm going to take u as the either negative st. So that means dv will be f prime of t dt. Okay, that means u du equals negative s e to the negative st dt. And v is the integral of this. What's the integral of the derivative of something? Isn't that the function that we differentiated, right? Integration in parts. U times v, that is e to the negative st f of t evaluated at from 0 to infinity. All right. And what's next? Minus the integral, oops, minus the integral from 0 to infinity of, what do we have? Negative s e to the negative st f of t dt. All right. So, well, number one, negative times a negative equals to positive, and well, let me actually set up the limit, maybe. Okay, yes, I'm going to set this upper limit of integration with a limit instead this time. Okay, so this will be a limit as b approaches infinity of e to the negative s b f of b. Okay, so minus e to the negative s of 0, f of 0, all right, plus s integral of from 0 to infinity of e to the negative st f of t dt. All right, okay, so where is this limit going to go? Well, guys, we can safely say that this is going to go to 0, right? Because actually the exponential function will dominate, right? And you may argue about, but wait. What if the function we're multiplying this exponential by is fast, it grows faster than the exponential? But guys, what did we say about the existence of the Laplace transform? Isn't it true that it has to be of exponential order, which means the exponential function dominates, all right? So e to the negative infinity, boom, that goes to 0, all right? E to the negative s times 0, which is e to the 0, that's 1, all right? So this will end up being negative, okay, equal to negative e to the, okay, negative f, no, negative 1, okay, negative 1, wow, come on, negative 1 times f of 0, whatever that is, plus s times, hey, do you recognize this integral here? Isn't that the definition of the Laplace transform? All right, which, yes, we can very well say fancy L of f of t, but isn't that the same as saying, well, actually, this is the Laplace transform of f of t, which is f of s. Well, rearranging this, this is s f of s minus f of 0. And this actually proves the first formula. All right, guys, in a similar way, you can derive and prove the other two formulas. Do I want to do that? I don't think I want to do that this time. I mean, all you have to do, okay, let me just set it up for you. Letter B, that's the Laplace transform of the second derivative of t, that equals the integral from 0 to infinity of e to the negative st f double prime of t dt. Just use an integration by parts approach. Somehow you will end up with the integral of e to the negative st, but f prime first. But didn't we already have the result from the previous part? So you can get these results recursively, iteratively. All right. I don't know if that's an actual word. I just made it up or something. All right. I mean, different iterations. That's what I. All right. Okay. So I mean, what we care about this is how do we use this to solve differential equations? I mean, what's the idea behind? Okay, so again, coming back to the idea behind the Laplace transform, which is an operation that transforms a function from one domain to a whole other domain. So the use of this Laplace transform is to turn a differential equation into an algebraic equation. We solve the algebraic equation for the function of s, find the inverse function, and boom, solution to the equation. All right? So, and that's pretty much what we're going to do. All right? Okay, use the Laplace transform to solve the initial value problem below. dy dt plus 3y equals to 3 sine 2t with y of 0 equals to 6. I mean, you could use the formula for linear first order differential equations we learned like in week 2 or 3, I forget, right? But I mean, we're going to use the Laplace transform in this case. So let's take the Laplace transform of the derivative dy dt, all right, plus 3 times the Laplace transform of y, all right, that equals the Laplace transform of 13 sine 2t, okay? So what was the transform of the first derivative? Wasn't that s f of s minus f of 0, okay? So this is s big F of s minus f of 0. Okay. And then what is the function? Actually, you know what? Because we're using really, I'm going to switch instead of f, I'm going to switch to y, right? Because I'm about to take the Laplace transform of y, which is plus 3 times y of s, right? Equals 13 times the Laplace transform of sine 2t, which is 2 over s squared plus 2 squared, which is 4. All right? Let's simplify things a little bit and substitute our initial condition. So y of 0 equals to 6. Substitute that here. Okay? And then number 2. 13 times 2 is that equals to 26. 26 divided by s squared plus 4. Okay? And what are we going to be left with on the left hand side? S y of s minus f of 0, which happens to be 6, plus 3 y of s. Okay? All right. So we have an equation. We still have an equation, but this is no longer a differential equation. This is an algebraic equation. An equation for which we're going to solve for y of s. Then we're going to take the inverse transform and boom, solution. Okay, so let me move everything to the right hand side of the equation that doesn't have any y of x. So I'm going to add 6 to both sides for that. And s y of s plus 3 y of s equals to 6 plus 26 over s squared plus 4, right? All right, how about we factor out y of s? So y of s equals times s plus 3, and that equals to, okay, I'm going to leave some space here. Okay, no, that's 6 plus 26 over s squared plus 4. All right. Okay, so we finally solve for y of s by dividing both sides by s plus 3 or multiplying by s plus 3. I prefer this. Okay, number 1. Let's go goodbye over here on the left side of the equation and multiply 1 over s plus 3 times 6. That is on the left hand side, 6 over s plus 3 plus 26 multiplying across 26 over s plus 3 s squared plus 4. All right? What will you do now? Find the inverse transform of this. All right? Um, However, finding the inverse transform of y of s equals the inverse transform of 6 over s plus 3 plus the inverse transform of 26 over s plus 3 times s squared plus 4. All right? So what about the inverse transform of 6 over s plus 3? Isn't that 6 e to the negative 3t? Right? And the inverse transform of 26 over s plus 3 times s squared plus 4, we would need partial fraction decomposition and do the whole process. However, didn't we do that already? Oh, wait. It was at the very end, right? It was this one, right? It was the term, it was all this madness here, right? Yep. So let me go back to this exercise. Okay, again, what did we get? Is that a 2, right? So 2 e to the 3t. Okay. From what exercise was this? Okay, let me go back real quick. That's from 1D, right? That was from 1D. Sorry to keep scrolling a lot. Okay. From 1D, okay. This is what was that again? Uh plus 2, okay, over s plus 3, okay. No, what s? Plus 2 e to the negative 3t, okay. Let me make some room here. And plus, or rather minus, 2 cosine 2t plus 3 sine 2t. And well, what's the inverse transform of y of s? Isn't that y of t again? And that's the solution to the differential equation, right? Let me recap on what we did briefly, and then we're gonna go to another example. All right. So we have a differential equation. Take the Laplace transform on both sides. The transform of the derivative s y of s minus f of 0 plus 3 times the derivative of the transform of y of t, which is y of s. And on the right hand side, the transform of 13 sine 2t. So that actually gives us a new equation to solve an algebraic equation. And we solve for y of s in this case, right? um, that's going to give us a right-hand side to find the inverse transform of. So for the first term, we got 6 over s plus 3, which is this term. And I believe there was supposed to be a plus 2 here, right? And I forgot something here. Combine these two together, 8 e to the negative 3t minus 2 cosine 2t plus 3 times sine 2t. Final answer, right? That's our very final answer. Let's do another example. Okay, so for the next example, we're going to solve a second order differential equation, unlike this one, which was a first order differential equation. Okay, so for the second order, we're going to need the if we go back to what is that, page 4, so we need the transform of the first derivative, and we're going to need the transform of the second derivative. Okay, so let's keep those in mind and go and solve the next example. All right. Okay, so let's take the transform of y double prime plus, or rather minus 3 times the transform of y prime plus 2 times the transform of y. All of these are functions of t. All right. So what was the transform of the second derivative? We say it is s squared y of s minus s y of 0 minus y prime of 0. So that's just the first term, the Laplace transform of the second derivative. Minus 3 times the transform of the derivative, which is s y of s minus y of 0, okay? Plus 2 times the transform of y, which is simply y of s. And on the right-hand side of the equation, we're going to find the transform of forgot to write the right-hand side, the transform of e to the negative 4t, okay, which is um, 1 over s minus negative 4, which is plus 4. All right. So that's the algebraic equation to solve for y of s. Isolate y of s and find the inverse transform on the right on both sides rather. All right. Okay. So number one, let me highlight some information here. So y of 0 equals to 1. This is the y of 0 we're going to substitute here. There's another y of 0 here to substitute. Yes. Number two, that is y prime of 0 equals to 5, which is this y prime of 0. Substitute the numerical values and let's do the algebra here. All right, so s squared y of s minus s times 1, that's just s, minus 5. Okay, let me make sure that my 5s look like actual 5. They can be confused with s's. If something looks weird, let me know. Okay, and then minus 3 times sy of s minus minus equals to plus 3 times the value of y of 0. But what's the value of y of 0? Isn't that 1? 1 times negative 3, I mean 1 times 3 equals to 3. Okay, that's fine. Nothing else to do. And simply plus 2 y of s. Okay? Okay, let's move everything containing or I mean, not containing a y of s to the right-hand side of the equation. Well, actually, I'd like to combine like terms first here. Okay, so that's s squared y of s minus s, and then negative 5 plus 3. Is that well, actually, I have a better idea here. Check this out. Check what I'm going to do here instead. Let me Let me highlight all terms containing the y of s. I think it would be better and even more efficient than keep writing the whole thing, right? So the right-hand side, it's still 1 over s plus 4, okay? So actually, out of these three terms in highlighted with yellow here, I can factor y of s, right? Already. So that is s squared minus 3s plus 2. And then over here, negative 5 plus 3 is at negative 2, which is minus s mm, minus 2 equals to 1 over s plus 4. Okay, 1 over s plus 4. Okay, let me move these two terms, negative s minus 2, to the right-hand side with opposite signs. Y of s times s squared minus 3s plus 2 equals to s plus 2 plus 1 over s plus 4. Okay. And we are a couple of steps away to get the y of s by itself. Let's just divide both sides by, or rather than dividing both sides, I'm going to multiply both sides by the reciprocal of this polynomial in s. So that is 1 over s squared minus 3s plus 2, okay? 1 over s squared minus 3s plus 2, okay? Well, these go goodbye, cancel, cancel, and y of s equals to, okay, distributing this s plus 2 times this fraction that equals 1, or rather s plus 2 over s squared minus 3s plus 2, and multiplying across 1 times 1 equals to, is that equal to 1? Let me leave some room over here. You'll see why. Plus 1 over multiplying across s to s plus 4. Well, actually, no need for this extra step. Yeah, no need. S plus 4, s squared minus 3s plus 2. All right. Yes, it looks like a monster to find the inverse transform, right? Hold on. Let's actually factor all the denominators here. So that is y of s equals to s plus 2 divided by the factor form of the denominator, which is factors of 2 that add up to -3. Are they -1 and -2? Plus s plus, oh, here we need extra space. Oh, come on. S plus 4, s minus 1, s minus 2 times 1 in the numerator, right? So I think I'd rather combine these two fractions together. All we need is, what is that? All we need is multiply numerator of the first fraction by the missing factor, s plus 4, s plus 4. Now that we have the same denominators, we can combine everything into one single fraction, all right? So that is y of s equals to uh, s plus 2 times s plus 4 plus 1, everything divided by the new denominator, s plus 4, s minus 1, s minus 2. All right? I think I would like to FOIL the numerator because you'll see why in a second. Okay? So I'm going to keep on this line right here. So s squared plus 4s plus 2s plus 8. And then don't forget this plus 1. Everything divided by s plus 4, s minus 1, s minus 2. Well, there's no more quadratic terms. Okay, that's y of s equals to s squared plus 6s plus 9. Everything divided by s plus 4 times s minus 1, times s minus 2. Okay, so we have simplified the right hand side. That's just a function of s. How about we find the inverse transform of this? All right. So finding the inverse transform of y of s equals the inverse transform of this humongous fraction divided by s plus 4, s minus 1, s minus 2. But A, didn't we already find the inverse transform of this fraction? In example, this is the one we did for Heaviside expansion. That is, let me go back here, page 3. We already found that inverse transform, so let's just use that result, okay? Unless you want to do it again, either doing the Heaviside expansion again for practice or partial fraction decomposition, no problem. The inverse transform of y of s is y of t. Finally, the solution. The solution is -15 over 6 e to the t plus 25 over 6 e to the 2t plus 1 over 30 e to the -4t. Final answer. All right. Okay. It seems like this was the last example, right? So let's call it for the section, okay?